Welcome back, everyone. This is Mr. Tanner, your instructor for sixth grade science. Looking forward to a great semester of learning. And our first notes for this unit are going to be about the scientific method, which is another way of saying what is science. So without any further delay, let's go ahead and get started with our notes. At its most basic, science is a method, which just means a series of steps. A method is a series of steps. And this method allows us to answer questions based on observations that we have made. So this method lets us answer questions based on observations we've made. For example, if I've made an observation that there's many different types of paper airplanes, and I've noticed that some paper airplanes have really wide wings and other paper airplanes have really narrow wings, I might ask, which type of paper airplane will fly further in the air? Will a paper airplane with wide wings or will a paper airplane with narrow wings fly further? And this could be a valid question based off of an observation. And it's one that you will explore in this first unit. It's also important to know that even though I'm going to lay the scientific method out as a step-by-step method where you go from step 1 to step 2 to step 3 to step 4, in reality, it's not quite like that. In reality, we might move backwards a couple of steps. Maybe an experiment we designed didn't end up working well, and we need to go backwards and design a new experiment. Or maybe we need to go outside of this series of steps and talk to other experts in other fields and get their input. Or maybe other experts don't agree with our conclusion, and we need to go back with them and look at our data again and form a new conclusion. So even though I'm going to lay this out as a series of steps, keep in mind that when we're doing science in real life, often we're moving backwards through these steps and then back forwards, or we might leave the steps entirely to talk to other experts and get their opinion before we keep moving through these steps. So it's not quite as simple as I'm laying it out here. So having said all that, the first step of the scientific method is to ask a question. Ask a question. And we need to ask this question, like I said earlier, based on an observation that we've made. So that would be like the paper airplane observation in question that I talked about on the last slide. The second step is to design an experiment. So in order to answer that question, we need to design an experiment that will allow us to answer that question. So for the example of the paper airplane, a possible experiment that I could design would be to make an airplane with wide wings and to make a paper airplane with narrow wings, throw each of them in as close to the exact same way as possible so that the test is fair, and measure how far they fly in the air. If I did that test multiple times and looked at how far they flew, I could probably answer that question by doing that experiment, and you, in fact, will be doing that experiment. The third step of the scientific method is to make a prediction about what you think will happen when you run that experiment. So you want to make a prediction that you're testing. So in the case of the paper airplane, I might predict that the narrow-winged airplane will fly further, or I might predict that the wide-winged paper airplane will fly further. Either one is a valid prediction, but in the science language, we don't call this a prediction. We call this a hypothesis. So we need to write a hypothesis where you predict what you think will be the answer to your experiment. And often when we're first being introduced to writing hypotheses, it's helpful to write these as an if-then statement. So I might say, if, and you don't need to write this down, just follow along. If I throw a paper airplane with wide wings and one with narrow wings, comma, then, so here's our if, here's our then, the airplane with, and I'll just say narrow for the sake of argument, with narrow, but remember you could also say wide. You need to choose one, don't put both, narrow or wide, with narrow or wide wings will fly further. So there's an example of a hypothesis as an if-then statement. If I throw the paper airplane with wide wings and one with narrow wings, then the paper airplane with either the narrow wings or the wide wings, you would choose just one, will fly further. In the scientific method, step 4 is where the real fun begins, because with step 4, we get to test our experiment. So you actually get to test your experiment here. So in this step, it's important to remember that you are trying to prove your hypothesis wrong. Trying to prove your hypothesis wrong. And let me explain why this is so important. Humans have what's called a confirmation bias. We want to be right. And it's innate in all humans. It's much better feeling to be right than wrong. So when we make a hypothesis, it would feel better if our prediction was correct. That would always feel better. But that may lead to us doing things to ensure that it's correct. So if I predict that the wide-winged airplane will fly further and I'm trying to prove my hypothesis correct, I might throw the narrow-winged airplane towards the ground a little bit. Or I might not fold it as carefully as I folded the wide-winged airplane. I might do some things that would make it more likely for the wide-winged airplane to actually go further. If I'm trying to prove my hypothesis wrong, if I'm trying to disprove it, I will make sure I'm being a lot more fair. If I happen to be right, that's great. But it's also great if I'm wrong. And this is what I always tell my students. If you make a prediction and your prediction is right, you haven't learned anything new. You just confirmed something that you already knew, which is exciting, but it's not that great. You haven't learned anything new. If you can prove your hypothesis wrong, you've now learned something that you didn't expect. That's way more exciting to hypothesis be wrong. I thought the narrow airplane would go further, but the wide one went further. So exciting. Or I thought the wide airplane would go further, but the narrow one did. That's really exciting. Learn something that you didn't expect. It's totally fine for your hypothesis wrong. And in fact, you want to ensure that you have every chance of proving it wrong so that we don't have a confirmation bias. So I'm not throwing any of the airplanes differently. I'm going to throw them exactly the same. And whatever the results is, then I can be more confident that I'm not trying to confirm my hypothesis. Remember, we're trying to prove it wrong. Step 5 of the scientific method really happens while you're doing the experiment. But while you're testing your experiment, whatever that experiment may be, we need to make observations and we need to record those observations. So record and observe. So I'm going to also record data. So record your data and your observations from the experiment. And here's the difference between a data set and an observation. When I'm testing my airplanes, my data will be how far they fly in the air. So my data might be that the narrow-winged airplane flew 10 feet and the wide-winged airplane flew 7 feet. That's data. It's usually actual numbers that you're looking at. Observations might be describing how it flew. Maybe the narrow winged airplane flies faster, but doesn't stay in the air as long. And you would say, it flew fast, but it also fell quickly. And maybe the wide winged airplane observation is that it flies much more slowly, but it stays in the air longer. Maybe this would happen. The wide winged airplane stayed in the air. It flew much longer, but it turned, so it didn't go very far in a straight line. So you could talk about that as well in your observations. And then that can maybe even lead to a different experiment, right? We talked about going back and revising an experiment. That's not the experiment we'll be running, but there's different experiments that you can conduct based off of the observations from your first experiment. So you need to make sure you're recording your data and your observations while you're testing that experiment. And then finally, the last step, which I think is the most important, but it also has the most capability to go wrong, is to analyze your data and form conclusions. So actually, I'm just going to cross that out, and you can just write analyze and conclude. So you're going to analyze your data, and you're going to write a conclusion. So analyzing your data and forming your conclusions. And the most important, I'll give you an example. The most important part of this is to use your data to support your conclusion. So this first example, you don't need to write down either the first or the second example. The first example would be a very bad conclusion. It might be right, but it's not written well. If I just wrote the narrow plane went further, that might be true for your data, but that's not a very good conclusion. We wouldn't want to write it like this because I'm not using any data to support that conclusion. Instead, I would want to say something like the narrow plane went further. I know this because on average, the narrow plane flew 20 feet, while the wide plane flew 12 feet. Now, not only am I telling you the conclusion, but I'm telling you how I know that conclusion is true. I've supported my data. I've calculated averages using math, right? So maybe you need to take multiple throws and average the distance for each of those. And I've explained in my conclusion that that is, in fact, what I did. I averaged the distance of the narrow plane. My data is that it flew 20 feet. The wide wing plane flew 12 feet. Hopefully, we can all agree that 20 is larger than 12, which would mean the narrow plane went further. So again, this first example here, the narrow plane went further, that is a terrible conclusion. It will not get you any sort of grade when we start writing conclusions for our experiments. Instead, I need to see that data, and I need to know how you came to your conclusion. So here's an example of that. I'm just really briefly summarizing those steps again. Step one, you're asking a question based off an observation you've made, and it's a question you want to know the answer to. Step two is designing an experiment that will allow you to find the answer to that question. Step three is making a hypothesis where you predict what the outcome of that experiment will be. Step four is to run the experiment. And remember, having your hypothesis be wrong is great. That's a very acceptable answer. So we don't want to try and make our hypothesis right. We want to make the test as fair as possible. Step five happens at the same time as step four, where you're recording all of the data from your tests. and recording observations that are happening while you're testing your experiment. And then step 6 is where you analyze that data and then you make a conclusion while you support your data. You support your conclusion with the data. This is the end of our scientific method notes. As always, if you have any questions or something from this didn't make sense, or you just have a question that relates to this loosely, please don't hesitate to ask. I love giving more information. Science is a passion of mine, and I hope that it will become a passion of yours as well. Until next time, thanks.